Neutrinos are among the most abundant particles in the universe, yet they remain nearly invisible to us. Right now, enormous numbers are passing through your body every second, and almost none of them leave any trace. This strange behavior comes from their fundamental properties. Neutrinos carry no electric charge, so they do not respond to electromagnetic forces the way electrons do. They also do not feel the strong force that binds quarks inside protons and neutrons. That leaves only the weak force and gravity. Gravity is effectively negligible at particle scale, and the weak force acts over extremely short distances with tiny interaction probabilities. The result is a particle that can cross huge amounts of matter almost undisturbed. This is why neutrinos can pass through the Earth as if it were mostly empty space. Their invisibility is not mystical, it is a direct consequence of how nature's forces are structured at the smallest scales. In the particle family tree, neutrinos belong to the leptons. There are 3 charged leptons, electron, muon, and tau, and each has a neutrino partner, electron neutrino, muon neutrino, and tau neutrino. These are called flavors. Flavor is not just a label for convenience, it describes how a neutrino is produced and detected in weak interactions. If a reaction creates an electron alongside a neutrino, that neutrino is born as an electron flavor state. For decades, physicists believed neutrinos might be massless. Their masses are so tiny that early experiments could not detect them directly, and simplified theoretical frameworks did not require mass. But measurements eventually showed neutrinos must have non-zero mass. Even a tiny mass matters enormously in physics, because it means the earlier version of the Standard Model is incomplete. Neutrinos therefore sit at a crossroads, they are part of known physics, but they also point beyond it. To understand why neutrinos are so difficult to observe, it helps to compare them with familiar particles. Shine light through matter, and photons interact frequently through electromagnetic processes. Send strongly interacting particles, and collisions happen readily in dense material. Neutrinos are different. Their weak interactions are rare, so most neutrinos simply continue in straight paths without scattering. Detecting them is therefore a game of probability. You need immense target volumes, sensitive light sensors, and long observation times to catch just a tiny fraction of interactions. That is why neutrino detectors are often built deep underground, inside mountains, in mines, or in polar ice. The surrounding rock or ice blocks many unwanted background particles, especially cosmic ray products, allowing the rare neutrino signals to stand out. Neutrino science is less about seeing every particle and more about collecting enough rare events to infer patterns, energies, and origins with statistical confidence. The discovery that transformed neutrino physics is called flavor oscillation. A neutrino created as one flavor can later be measured as another after traveling some distance. For example, an electron neutrino produced in the Sun may arrive at Earth and interact as a muon or tau neutrino. This happens because flavor states are quantum mixtures of mass states. A produced neutrino is not traveling as one single mass identity, it is a superposition of several mass components. As these components propagate, their quantum phases evolve at slightly different rates because their masses differ. Those phase differences shift the flavor probabilities over time and distance. Oscillation is therefore a wave-like quantum interference effect. Most importantly, oscillation cannot occur if all relevant neutrino masses are exactly the same in the required way. So once oscillation was confirmed, the conclusion was unavoidable: neutrinos have mass, and our baseline theory had to be expanded. Even after confirming neutrino mass, major unknowns remain. Oscillation experiments primarily measure differences in mass squared values, not the absolute mass of each neutrino. Think of it like knowing the spacing between rungs on a ladder without knowing where the ladder starts from the ground. We can determine relative structure very well, but the absolute scale is still difficult. Another open issue is mass ordering, whether the third mass state is heavier than the other two in one pattern or in an alternate arrangement. On top of this, Cosmology places strong limits on the total neutrino mass because neutrinos influence how structure forms across the universe. Large-scale galaxy distributions and cosmic background data constrain how much mass neutrinos can collectively carry. Laboratory measurements from beta decay provide complementary constraints. Together, these approaches have narrowed the possibilities, but not closed the case. Neutrino mass remains one of the most important precision frontiers in modern physics. Every neutrino has a corresponding antimatter partner called an antineutrino. Both are electrically neutral and both have spin 1/2, but they differ in key quantum numbers such as lepton number, and they participate differently in weak interactions. In weak processes, neutrinos are associated with left-handed chirality and antineutrinos with right-handed chirality. This asymmetry is central to the structure of the weak force. It is also why beta decay channels are tightly constrained. Particle combinations must satisfy conservation rules, including lepton number bookkeeping. Distinguishing neutrinos from antineutrinos in experiments is not always simple, because detectors often infer identity indirectly from interaction products. But the distinction is crucial, especially in long baseline experiments that compare neutrino and antineutrino oscillation behavior. If measurable differences appear beyond expected effects, they could signal CP violation in the lepton sector, a possible ingredient in explaining why the universe ended up with far more matter than antimatter. Neutrinos are produced in many environments, from ordinary radioactivity to violent cosmic events. In stars, nuclear fusion chains generate neutrinos continuously. Because neutrinos interact weakly, they escape stellar interiors almost immediately, carrying direct information from core processes. In supernovas, neutrino emission is extreme. A collapsing star can release most of its gravitational energy as neutrinos in a brief burst. On Earth, radioactive decays within crust and mantle create geoneutrinos, offering clues about internal heat production. Human technology adds controlled sources. Nuclear reactors produce intense antineutrino fluxes from fission fragments, and particle accelerators generate neutrino beams with tunable energies for precision studies. Cosmic rays striking Earth's atmosphere create additional neutrinos, forming a natural high-energy laboratory. This diversity of sources turns neutrinos into universal messengers. They appear wherever nuclear transformations and high-energy interactions occur, giving scientists a tool to study processes that are otherwise obscured or inaccessible. Near Earth, the Sun dominates the neutrino background. The flux at the planet's surface is immense, around tens of billions per second per square centimeter. Early detectors, however, found fewer electron neutrinos than solar models predicted. This became the solar neutrino problem, one of the major puzzles of 20th-century astrophysics. Two broad explanations competed: either our model of solar fusion was wrong, or neutrinos were changing identity in flight. Over time, new detectors with different sensitivities resolved the puzzle. The Sun was producing the expected total neutrino output, but a significant fraction of electron neutrinos transformed into other flavors before reaching Earth. That result simultaneously validated stellar fusion theory and confirmed neutrino oscillation. It was a landmark because it united astrophysics and particle physics around a single coherent explanation. Neutrinos, once considered nearly irrelevant due to their weak interactions, became decisive. Evidence for both how stars work and where existing particle theory needed revision. How do detectors actually catch a neutrino if interactions are so rare? They watch for secondary effects. In water Cherenkov detectors, a neutrino interaction can produce a charged particle moving faster than light travels in water, generating a cone of blue Cherenkov radiation. In liquid scintillator detectors, interaction products excite molecules that emit flashes of light. In deep ice arrays, sensors capture faint light from charged tracks created after neutrino collisions in or near the ice. By measuring timing, intensity, and geometry of these light signals, scientists reconstruct the incoming neutrino's energy and direction statistically. Each detector type has strengths and limitations. Some excel at lower energies, others at high-energy astrophysical neutrinos, some have better directional precision, others stronger flavor sensitivity. Because signals are sparse and backgrounds can mimic events, calibration and analysis are rigorous. Neutrino detection is therefore equal parts instrumentation, data science, and fundamental theory. Neutrinos are now practical probes, not just theoretical curiosities. Geoneutrino measurements help estimate how much radioactive decay contributes to Earth's internal heat budget, improving models of mantle convection and planetary evolution. Reactor antineutrino monitoring offers potential non-intrusive support for nuclear safeguards by linking measured spectra to reactor operation conditions. In astronomy, neutrino detectors can provide early alerts for nearby supernova collapses, because neutrinos escape before visible light fully emerges. At the highest energies, cosmic neutrinos trace extreme astrophysical accelerators and complement information from photons and gravitational waves in multi-messenger studies. Their weak interactions, once a detection obstacle, become an advantage in propagation. Neutrinos travel vast distances with little absorption or deflection, preserving directional and temporal clues about their sources. In that sense, neutrinos function like deep penetration messengers, carrying information out of dense environments and across cosmic scales that would scramble or block most other signals. The next era of neutrino research targets several profound questions at once. What are the exact absolute masses? Which mass ordering is correct? Do neutrinos and antineutrinos oscillate differently in a way that reveals CP violation? And perhaps most fundamentally, is the neutrino distinct from its antiparticle? Or could it be a Majorana particle, meaning both are the same entity under the hood? If neutrinos are Majorana, rare processes such as neutrinoless double beta decay might occur, violating lepton number and opening a route to new physics mechanisms connected to matter-antimatter imbalance in the early universe. Future progress will depend on combining giant next-generation detectors, precision accelerator beams, improved reactor experiments, and tighter cosmological measurements. Neutrino physics began as an attempt to account for missing energy in beta decay. Today it stands as one of the sharpest tools for testing the limits of the standard model and exploring what lies beyond. If you found this helpful, please like this video and subscribe for more explainers.